All right, so here is a titration curve of a weak acid and a strong base. So it looks a little bit different than that last titration curve we have. Notice that we start with a higher pH, so it's not as low. So this is starting with a pH of about like 4 or 5. And when we look at involving something that's weak, know that we're going to have a stronger buffering region than we would with a strong acid, strong base. And the maximum buffering region we're going to find at the halfway point. So it's called the halfway point. It's the halfway point to the equivalence point. So, and you read it with the volume down here at the bottom. So if I know that my volume, let's say, was 20 milliliters, then my halfway point would be at 10 milliliters. Okay, so let's look at the different points of the curve. So first of all, I have a starting pH, and you know how to figure that out. So you would have to be given the Ka, and then you would use that Rossiter equation to help you find it. So remember the Rossiter equation, which is the concentration of the hydroxide, the Ka, and then I have my acid on top, and then my conjugate base on the bottom. Okay, so you could find the pH through that. After you did that, then of course you'd have to take the negative log of the hydrogen ion. Okay, you also could use this formula, which is right here. That is on your data sheet now. They took it away for a little bit and it's now back. I still prefer to use the Rossiter equation. It's just less complicated, I feel like. So the maximum buffering region would be right here along this little gradually sloping curve. And again, at the halfway point, that is where the concentration of your acid would be equal to the conjugate base. And at that point, that is where you can figure out where the pKa is. So if these two are the same, so I can cross them out, then I end up with my Ka is equal to my H plus, or my pH is equal to my pKa. So I can find my Ka actually by reading the chart, by finding that halfway point. All right, so that's what's happening at the A. At B, that's your equivalence point. Notice for a weak acid, strong base, I'm going to be a little bit above 7. So maybe I'll say this is a 9. That's my equivalence point, so it's slightly basic. And then note up here, just to make the graph pretty, this is where excess base is. In a lab, you actually wouldn't ever do this. You just stop at the equivalence point. Again, how to find the halfway point is look where that straight up and down is, read the volume, and then divide by 2, and that's where the halfway point is. So at the halfway point, that's where I could find my pKa, and then to go from your pKa to your Ka, you would just take 10 to the negative pKa, and that would tell you what your Ka is. Here's just a picture showing this weak acid. So again, starting off with the weak acid, notice it's all together. Then in that buffering region, you can see that you have that conjugate base. At your equivalence point, that is where the moles of acid equal the moles of base. And we have just really the leftovers at that point, so it's completely made water. And then at the top, the very, very last picture, it just shows there's excess base. So that's where you see the OH. Again, to find the equivalence point, approximate where the little straight part is, and then read what the pH is in the middle. To find the Ka for this, I would go to the halfway point. So that would be 25 milliliters. And I go over here. And so my pKa would be equal to, let's say, 5. We'll just keep it easy. So that means to find the Ka, I would do 10 to the minus 5. So my Ka, I can read from the graph, it would be 1 times 10 to the minus 5. So on the AP test, you need to be able to know how to sketch a graph, how to get the Ka from the graph, how to determine if it's strong or if it's weak, what you're starting out with, if it's strong or weak, what you're titrating with, if it's strong or weak. And again, you shouldn't ever have 2 weeks together. So You could have one weak and one strong or have them both strong. Okay, I can do an ice chart. So I have acetic acid and it is going to dissociate into hydrogen ion and then the leftover. And I can start off with 0.1 of this and 0 of each of these. This is going to lose a little. These are going to gain a little bit. So I end up with this situation. Here's my ice chart. So I know that my Ka is equal to my H plus times my acetate ion divided by my acid. So this ends up being 1.8 times 10 to the minus 5 equals x squared over 0.1, because we're going to take the shortcut. This is tiny. If you just write that in your notes, you'll get credit for that. So I get x squared, and then I'm going to square root each side, and I have x is equal to 1.3 times 10 to the negative 3. And I'm going to take my pH. So my pH is equal to the negative log of my 1.3. And I get a pH at the start of 2.87. So we can see we're starting out acidic. This is a weak acid, but it's actually quite a low pH. It is possible that you can have a weak acid have a lower pH than a strong acid. It just depends on the concentration. Now this says what is the concentration of the NaOH. So for this, we would do this titration, and let's say we end up getting 10 milliliters in this titration. I'm just making this up because I'm not actually doing it. But it says what is the concentration of the NaOH. So this is the equivalence point, so I can use the moles of acid times the volume of acid equals the molarity of base times the volume of the base. And I'm going to just fill everything in. And I don't know my molarity, but I do know my volume is 10. So 0.1 times 50 divided by 10, I get a 0.5 molar concentration. Okay, and if I had to write an overall net ion reaction, doesn't say this, but we could write this out. So keep your acid together, then you drip in the hydroxide, that's the strong acid, and you're going to end up with water and your leftover, so your CH3COO minus. So there's your net ionic. The pH at the equivalence point, you don't need to find that, but if you were to sketch this out, so I would have it start at around 3, just below 3, okay, and then I would have it go up right here. This is at the 10 milliliters, and then draw it like this, and that equivalence point, you're going to make sure that this is above 7. So, and just approximate it. I mean, if it's up there 8 or 9, that's great. So if you had to sketch this out, so it's not required for you to know the final pH. They've taken that out of the program because it's a lot of math, and it doesn't really teach you the chemistry. Just gets you frustrated with the math. So the point is you should know this should be slightly basic at the equivalence point, and you should be able to sketch this graph. If asked, you should be able to figure out that pH, or excuse me, the Ka. And again, to take the Ka, you go to the half equivalence point, so that would be at 5. And then you'd read whatever the pH was and take it. And you can see that this has the exponent of 5. So that would be just about right. So that this is my pKa, which would be right around 5. And so there's my Ka. So if they gave you a graph instead of giving you what the Ka is, you should be able to read it from the graph. So reading some graphs, so you should be able to find the equivalence point. So again, find that straight up and down, and then approximate where it is in the middle. So this one's right around 8. You should be able to find the halfway point. So again, everything goes down, I don't know, 28. So let's say 14. So at 14, that's where I would read my pKa. So it's right around, I don't know, 4.5. So to find the Ka, I would do 10 to the negative 4.5 and then press enter. Okay. Let's see here. Again, this is where there's just excess. In normal lab, you wouldn't do this. It just makes your curve pretty. So these are all the points that you should be able to read from your graph. Oh, you should also be able to figure out what this is. This one tells us it's a weak acid and a strong base. So go ahead and stop the tape and go through and answer these questions. Okay, we're back. I'm laughing. I said stop the tape. That tells me how old I am. So stopping the video. All right, which type of titration is represented here? So this one looks like, well, my equivalence point is right around there. And it's above 7. So this means I have a strong base. So this is a weak acid, strong base. I'm starting with my weak acid. Here's my buffered region there. I can read the volume. Oh, we'll say 0.6 on this chart. So I would go to like 0.3. That would be the halfway. That's where my pKa is. Okay. At the equivalence point, this is where the moles of acid equal to moles of base. And did I answer all of them? At this point, the solution is buffered. So that's that buffered solution, that box I drew there. And I think I got all the questions. So see how you did. All right, this one's starting with the base. So it looks a little bit different. So on this one, my equivalence point is less than 7. It's right around 5. So because of this, I know that this is a strong acid titration because it ends up being a little bit acidic. And that's because the weak base has a stronger conjugate acid. So here's all the points. So we have buffering going on here. We have one drop adding and then it's going to this time swing wildly down. We can say our halfway point is at that 40. And so this time when I find the halfway point, it actually tells me this is my pKb because I'm starting with the base. So the halfway point, my pOH equals the pKb. I'm missing a P there. Okay, pKb. All right, so just kind of done the other way. They did one just like this probably 3 years ago. So I don't anticipate them asking you one of these. So probably do a weak acid strong base titration because they haven't done that for some time. What happens if you have an acid that has 2 hydrogens? So remember, if something has 2 hydrogens, like this is a typo right there, like this is carbonic acid, it loses its hydrogens one at a time, and we get a graph that looks like this. Notice it has 2 equivalence points. So they're not as straight up and down as you would like them to be. They're a little bit crooked. So you can see that instead of straight up and down, it kind of goes like this, but you can find it the same way. Go in the middle, and then you're just approximate. That is where the moles of acid equal the moles of the base of the first hydrogen. And then this, they didn't finish it off here. They just stopped at the equivalence point. So you can see that it's kind of a little bit more angled, but there's your pH of your second equivalence point. So probably just above 7 on this one. And on the AP test, that's all you have to do is identify what the equivalence points is, and you should be able to do each of the Kas. So go to the halfway point. So on this one, it'd be around 5. And then I would just read this as above 2. So maybe it's like 2.1. So I would do 10 to the negative 2.1. That would equal the Ka of the first one. And then on the second one, I would say the Ka of the second one is equal to 10 to the minus, I don't know, 7.5. Okay, and then press enter. So, all right, here's just some more practice that you can do. So go ahead and stop the video and figure out where all the Ka's are and figure out what the pKa's are. On some of them, the answers are there. I didn't block it out, but just see if you agree with those numbers. See if you can find it. Okay, we're back. So here are the answers. So as you look for each of these, again, look for some of these are not very strong. So for example, right here, that is not very strong, but there is one hydrogen being lost right there. Just one drop causes it. The moles of acid equal to the moles of base right there. This second one is more pronounced. So they all look a little bit different, but you should be able to tell what the Ka's for each one of them are, or what the pH is at each of the equivalence points. And this is just extra. Can you identify which each one of these are? Go ahead and stop the video and see if you can. Okay, we're back. So the first one is the strong acid and strong base. So I'm going to look for something that has a pH of a 7. And the only one is this first one. So that one goes there. Okay. This next one is a weak acid and strong base. So that means at the equivalence point, my pH should be above 7. And I should start with a weak acid. So it's this one. A weak base and a strong acid. Well, there's only one that starts out as a base, so it's that one. And then this one is my polyprotic one. So you can see there's 2 equivalence points. How do indicators work? So indicators work when a hydrogen is being lost and it causes a color change. So on this one, this is phenolphthalein. It's clear when it's in low pHs, but once it reaches around 8, then it's going to be pink. And they didn't color the whole chart in. Once you're past around 8, it's going to be pink the whole time. So it's going to look like this. So this is a good indicator if you have a weak acid and a strong base. And that's because the equivalence point is going to be slightly basic, because you want your indicator, your endpoint, to be as close as possible to the equivalence point. So this one works really well with strong acids and weak bases. I said it wrong. Weak acids and strong bases. How to choose the right indicator. So you want to figure out where the equivalence point is going to be and then pick the indicator it's going to turn at that color. So on this one, if you look at this curve, this is a weak acid and this is a strong base. So you can see my equivalence point is going to be right there, right around 8. And so I wouldn't want to use bromothiamyl green because it's going to change color when it's a pH of around 4 or 5. And that is not anywhere close to where that equivalence point is. I also don't want to use bromothiamyl blue. That one works best at a pH of around 7. So that one works great with strong acids and strong acids and strong bases. Okay. So the phenolphthalein, again, would work best with weak acids and strong bases because it's going to have the indicator change right around 8. So this is just a little chart that shows you the color. So again, you want the color change to occur at the correct pH. So if the AP board or me for like a problem on your test or in your packet, you would look at that pH range color, and then you would analyze and see, hey, I have a strong acid, I have a strong base, so I want something around 7. So you want to do something that's within 1. Okay, so if it changes color like at a 6 or like at an 8, and you know it's a strong acid, strong base, which is a 7 as the equivalence point, then that would be okay. So so you just want to get as close as possible to what that equivalence point is going to be. Okay, but I wouldn't want a color to change at a pH of 2 if I had an equivalence point at a 7. Anyway, so on this one it says which indicators would be useful for a titration between sodium hydroxide and nitric acid. So this is a strong base and a strong acid. So I know my equivalence point is around 7. So I'm going to use any sort of indicator that changes color around then. So within one pH point, okay? So I could use this one, but any of these, those would be ideal, okay? Let's do the next one. It says ammonia and HCl. So this is a weak base and a strong acid. So I'm going to end up with a pH of less than 7. So maybe a pH of like, I don't know, 5. So where's 5? 4 or 5. So come over here, and I would want to use any of these. Okay. So again, just as long as you're close. And then let's do the last one. So the last one, acetic acid is a weak acid, and that one is a strong acid. So that means my pH is going to be, and that's a strong base. So that means my pH is going to be bigger than 7. So like at a 9, again, we're just kind of guessing. So I would want to use any of those. Okay. So this is how you pick your indicator. If you have a diprotic acid, you would want to use a couple indicators, one that would change with the first equivalence point and then one that would change with your second equivalence point. So let's go through this. Choose the best indicator when the pH is at equivalence is 6. So again, you want to be within 1. So on this one, I would use litmus. That one seems to be the closest. And the pH at equivalence is 8.9. So I would use, it's pretty close to 9. So I'd probably use this one, okay? Thymolpethylene, okay? I'll just put T. And then the pH equivalent is 5.6. I don't think I'd use this one. I think that one's too far off, so I think I would use the litmus again. So that is how you pick your indicator, is based on what the equivalence point is.